This year, it's the turn of Stanford University's Professor Nick McCowan to talk about software-defined networks and the maturing of the internet. In your packs, you will find a more detailed biography of Nick, which lists a number of things that he has accomplished over his life, including working for Hewlett-Packard. He's also a member of the US National Academy of Engineering, a fellow of the Royal Academy of Engineering here in the UK, IEEE, and ACM. He co-founded both Nicira and the Open Network Foundation, and his day job is Professor of Electrical Engineering and Computer Science at Stanford University. So I'm very pleased, on behalf of the IET, to invite Nick to take the lectern and deliver the 2014 Appleton Lecture. Thank you.
Thank you. So I'm here tonight to tell you a story, and the story is about the internet, of course. So when you hear the word internet, you probably think of things like Google, Yahoo, Netflix, Amazon, things like this. And in fact, you probably heard in the last few months that the internet just turned 20. The truth of the matter is that the internet actually just turned 50. But what most of us know as the internet is the World Wide Web, which really came into prominence about 20 years ago when Tim Berners-Lee invented the World Wide Web. And then, of course, the rest is history, as maybe some of you saw on the slides earlier. I'm actually going to be talking about the internet infrastructure. That's the plumbing. And the plumbing of the internet started to be thought about and created in about 1964, almost exactly the time that this picture was taken, which is when my interest in communications started. I'm told that this was April the 7th of 1964, my first birthday. And it turns out that April the 7th is rather an auspicious date for the internet, as we're going to learn as we go through. But the thing that you will know of the internet, these applications, which is how we all use the internet, how I use the internet typically, we think of it as delivering a service from a laptop, a desktop, a handheld device, from some remote warehouse of computers called a data center, over which packets are delivered. I'm sure you all know this already, and that the internet has grown up as an infrastructure. But what I'm going to be talking about is the plumbing. And that's the infrastructure that sits underneath. And plumbing, like the plumbing in our houses, plumbing is best when it's invisible. You don't want to have to think about how the plumbing works, and you particularly don't want to think what happens when, not only when you turn on the tap, but flush the toilet. So plumbing is particularly effective when it's working. And the fact that you know probably more about how the internet works than you would like is because your experience is often it doesn't work, and it's not particularly effective. When it does work, it transforms our lives, it transforms society. But I'm talking about that plumbing, and that plumbing that I'm talking about is that which is shown in red, and so I'm going to get rid of all of those applications, and we're just going to focus on that internet plumbing infrastructure. And as you probably know, the internet is made up of routers, and Americans call them routers, and I apologize in advance if I slip into that, and links that interconnect those routers between two or many, many endpoints. And our typical experience is pulling packets across the internet through those routers and links in the form of packets. And those packets, they all look pretty much the same. They're a self-contained unit, and they are routed hop by hop across the internet by looking at the address, just like a letter is as it goes through the sorting system of the post office. So that packet, which has data and then has the address at the front, will be routed across router by router, and that's basically it. That's how the internet works. Now, in order to understand what I'm going to be saying for the rest of the talk, it helps to know that the internet, in its original form, as it was originally described and invented, is ridiculously simple. It was designed to be simple, dumb, and streamlined. And I want to talk a little bit about how it was originally conceived so that you can then see how different it is from how it has become. And therein lies a problem. And that problem is what I'm going to be talking about, and its solution, and how we hope that that solution will return the internet back to its simple, streamlined, and dumb form. So the internet was designed so that packets can be corrupted. So packets can go through, as this one did here, and be corrupted on their way, and the internet has to deal with that. So your application when it's delivering data to you has to deal with the fact that they could be corrupted. In fact, they could also arrive out of order. So here's 2 packets, 1 and 2, that the internet changed the order. They could also be duplicated. So this router here failed, and it happened to duplicate the packet it was passing through. And in fact, they may not arrive at all. So why was it that an internet that is so simple and so dumb, so successful? Well, it turns out, by luck, by happenstance, by some extraordinary visionary pioneers in the 1960s, that the internet was successful entirely because it was so simple and dumb. And if there's anything that I worry about that keeps me awake at night, it's that the internet is getting more and more complex. It's getting less and less dumb. And so it becomes less reliable, less secure, and therefore its growth, its possibility, becomes hindered. So how can it be that a network that was so dumb and so simple be so successful? The underlying network, and I'm going to describe here a technology or an abstraction that we use to describe the internet. The internet itself has what we call a network layer. The internet is arranged as layers of abstraction. So when your computer is sending packets on your behalf, on behalf of an application, so here are the applications at the top, it sends that down to a layer of processing, a layer of software, whose job it is to make sure that those packets are delivered correctly in order at the far end. That's its job. It's running in software sitting on this computer here. It's running right now. No doubt it's exchanging information with someone because I'm connected to the Wi-Fi, and your phones in your pockets are probably doing the same thing. So those packets go down, that information goes down, and eventually they're delivered as packets across the network to the other end, where they're delivered up through these layers until they eventually find their way to the application. So that transport, that thing called transport, it's also known as TCP, and if you've heard of the internet in another way it gets described as TCP/IP, the TCP portion is responsible for the reliable delivery, and that runs entirely at the endpoints, but the internet itself is that dumb, simple, streamlined substrate that sits underneath. It was designed to be that way, and it was beautifully described by someone called David Clark, who was also born on April the 7th, who was chief protocol architect for the internet throughout the 1980s, in a paper that I would encourage many of you who are interested in this to read. It's very, very accessible, very, very readable paper. It's written in August 1988 as a retrospective of why the internet was designed the way it was. It was starting to be very successful. At that time, it was known as the DARPA internet, because it came from the US Department of Defense. But it was being described as to why it was designed that way. And we refer to it as having certain architectural principles that guided its design. And I want to highlight 3. The paper had 8 architectural principles, but there are 3 in particular that have turned out to be extremely important. The first one is that it be dumb and simple, and I've already mentioned this. The consequence is that the network itself would be streamlined, it would be fast, it would be low cost, it would be easy to maintain, and it would require infrequent upgrades. Because if all of the equipment is buried in the ground or buried in buildings across the country, then it's very hard to upgrade. Much easier if you can just upgrade it at the edges. So by putting all of the intelligence to the edge, where the reliable in-order delivery would take place, built on top at the endpoints, then you could keep that network dumb and simple. So the intelligent endpoints, coupled with a dumb and simple network, were an important characteristic, an important architectural principle. The third one that I want to mention is decentralized control. There is nobody who is in charge of the internet. Well, maybe the NSA is in charge of the internet, but we don't know about them. But there is no authority that is actually responsible for the management and control of the network, only the addresses. This was a very important distinction. It was very different from any network that had ever been built before, where centralized control and centralized management was taken as a natural and the only way of doing things. The consequence of this was that bits of the network could grow, managed by different people. In the US, they say mom and pop shops, so they were little pieces of the internet would grow because people could just manage it on their own. They didn't have to answer to some central control. As a consequence, as you might imagine, and as we know, there was very, very rapid organic growth. So when the internet started, in terms of deployment in 1969, it consisted of 4 nodes. There's a picture of it as it was at that time in 4 parts of California. As more internet was added to it, it became bigger and bigger and bigger, and we know that story until it looks somewhat like this. This is actually a diagram of the structure of just the core of the internet as of 4 years ago from a project called the Opti Project that tries to keep in touch with these things. As well as that rapid organic growth, of course, the number of computers connected to the internet grew as well. No point in having a network without the end hosts. And the number of end hosts has continued to grow. And you've seen this graph before, I'm sure, all the way back to 1993. It appears to be 0. It was of the order of about 100,000 at that time. And it has grown continually until in 2013, it passed 1 billion computers attached to the network. So, summary so far. The internet was deliberately designed to be simple and streamlined, to have decentralized control, which meant lots of individually controlled pieces, which led to an explosive organic growth of the internet and also a great business opportunity for those who sell routers. And this is important. It's important that somebody is making money in order to be able to keep the innovation going and keep that piece of the infrastructure built. So, what do you do if you're in a business for which it's important that it's simple and streamlined, and you want to keep it as a great business? Simple and streamlined means low barrier to entry for competition, very simple for others to enter into that market. And so it becomes a commodity or a utility. And you'll remember in the 1990s, the internet was going to become a utility. The internet as a whole. So what do you do if you're in a business, as the router vendors were at that time, a 70% gross margin business, which means for every £100 of equipment that they're selling, it only costs them £30 to make it. So what do? Do you just say, oh, well, it's going to go simple and streamlined, and I'll allow that to happen, and I'll go off and do something else? Or do you try and prevent that from happening? And I'm not suggesting a conspiracy here. It's just the natural order. That's what probably all of us would do in their shoes. And so the industry as a whole set out, naturally or intentionally or accidentally, who knows, to try and make the network more complicated. Because it's the only way to establish a barrier to entry for others. This was directly at odds with and directly in collision course with that original simple, dumb infrastructure. And so one measure of this is the number of published internet standards that represent features on those boxes. This is the number of published internet standards since, in fact, the first one was April 7th, 1969, was published on that date, and ever since we've reached 7,000. And as you can see, it doesn't show much sign of stopping. Most of these were written and funded by the router equipment manufacturers themselves, because they are the ones that know the technology best. They are the ones who are in the position to publish these standards and come up with these new ideas. And naturally, the stock price of the largest one, but it seems true for all of them, grew 200x in that time. So the consequence of this is very, very serious for the internet, which is a very important part of society today. It means that those routers, of which I just show a picture of one here, this one happens to be built out of 3 boxes. Each one costs about $1 million. It's about the same size as me, 6 feet tall, about 2 feet wide, and generates, in my case, I generate about 1 kilowatt. This one will generate about 15 kilowatts. They're very, very big pieces of equipment. Very complicated, and they consist of, in software, about 50 million lines of code. So that simple, dumb internet became something which was 5 times more complicated than the most complicated piece of telecommunications equipment ever built before. It's based on hardware which consists of tens, hundreds of billions of transistors. They are fragile and insecure in that they are security nightmares. They are bloated and power hungry. And essentially, they're like the computer mainframes that we knew of the 1960s. So in that time, that computers became easier to use and more reliable. So here a picture of a computer from the 1960s. You remember these things? The IBM PCs? Do you remember AutoExec.bat? Well, that's been replaced over time with a computer that you don't really have to think about how it works, accessing servers in a data center somewhere, and now a handheld device. I haven't switched mine off in months. I just rebooted this laptop for the first time in about 3 months. So now we just take that reliability for granted. So in the time that computers have become easier and more reliable, the networks have become harder and less reliable. The software industry that was behind making computers more reliable has many, many tools at its disposal. They've developed many tricks, many tools, many techniques. And there's a rich mathematics associated with software correctness. I won't go through how all of this works, but it would take months to go through and do even justice to a little bit of the software engineering industry as it exists today. So there's about a $10 billion a year tools business of selling tools to improve the quality of software, which is supporting about a $300 billion software industry. And if you look online, you'll find hundreds of books, hundreds of thousands of papers, research and academic papers, and tens of classes that you can take at universities about software engineering. It's a rich academic field, and it's well understood. The networking industry, on the other hand, which is also about a $300 billion industry, basically has 5 tools. If I can get this thing to work, I'll show you one of them. How many of you ever used Traceroute? Smart bunch. So for those that haven't, oh, okay, maybe I shouldn't do this. Maybe I'll go back to, let me just go back to this. I was just going to show you a Traceroute for those who haven't seen it. Most of you have. They're basically a set of very rudimentary tools that we can use for managing the network. And this is the same set as 10 years ago. It's the same set as 15 years ago. Really, that's about it. And networks today are kept working by so-called masters of complexity. This is a phrase that my colleague Scott Schenker at Berkeley adopted as a way of describing people who usually got ponytails, and they have mastered the art of keeping networks and computers going. And they're fantastic. They've got a wonderful experience. What they do is they send probes of packets through the networks, and then they pattern match with extraordinary ability to look for trends or problems that they've seen before, maybe many years ago. It's an incredible art. It should be completely automated. There is no reason why it shouldn't be, except that the equipment itself is far too complex to allow that to happen. I'll explain a little bit more a bit later. There's really no books. I can only think of 1 or 2, almost no papers, and you certainly can't take a class in how to manage a network at any university. So complexity means networks have become too expensive to own and operate. And I want to give you 2 examples of why this, of people who are suffering or organizations that are suffering because of this. Now, it's not often that we cry for the phone companies or the internet service providers, but on this one, actually the odds are stacked against them. So if you are an internet service provider like British Telecom or Deutsche Telekom or AT&T in the United States today, then you're facing with a global IP traffic which is growing at about 40 to 50% per year. The end customer, that's us, is paying a monthly charge of, what, £20 for internet access? And we're certainly not planning to pay 40 to 50% more next year, even though we're generating 40 to 50% more traffic as we watch more videos. We're expecting to pay less. We have this expectation that the price will go down. So therefore, the cost of ownership for the internet service provider must be reduced by 40 to 50% per bit per second, per gigabit per second that they carry per year. In practice, they're doing a pretty good job, and they're reducing it maybe by 20%. I think actually in practice it's less than this. What is the consequence of that? Well, pretty obvious what's going to happen over time. That £20 per month, that revenue that we're expected to go down, the growth in traffic is something like this. If you then account for that 20% reduction in cost per gigabit per second, then the total cost might look something like this. That point there is very scary because it means there's no profit. The cost outstrips the revenue that you're gaining. And there's really not much other business to be in if you're an internet service provider. So they have a very strong vested interest in reducing the cost, making the network simple, making it do only the things that they need it to do, taking more control over the functionality, taking more control over the features, stripping out the features that they don't need, reducing the power so they save on their electricity bills, and being able to differentiate, which means that if I am British Telecom trying to compete with Deutsche Telekom for, say, Reuters business, I'd like to be able to provide a different service from them so I can compete. So I'd like to differentiate the service that I provide. But given that all of the functionality is controlled by the sellers of the equipment, then there isn't the opportunity to differentiate. And so I can't provide a different service because I'm forced to provide the same service as the other. As a consequence, I can't charge more, and therefore I can't get out of this problem. Fortunately, the folks that are coming to their rescue are the people that they fear the most, and that's the owners of the data centers. So here's a cartoon picture of a data center, lots of servers at the bottom, switches in the middle, links to bigger switches on the outside, and these are the kind of data centers that your Google search goes to or where you stream a video from. The first rationale for the data center owners to change networking, and indeed they are the ones that are bringing about the most change, is cost. They build data centers today, the bigger ones, have about 400,000 servers in them, nearly 500,000 servers. Those servers are connected together in one data center by about 20,000 switches. The market price for a switch from a conventional vendor is about $5,000. So that means just for one data center, the switches in that data center cost about $100 million. If instead, let's say, they could drive the price down to $1,000 by designing them themselves, and if you're going to save that much money, it's probably worth it, then they can save they can reduce that to $20 million for one data center, and if they're building about 10 data centers per year, then they're going to save $800 million. So you can employ a lot of people to make it worthwhile to build your own networking equipment and not have to buy it from others. And this is exactly what's happened. So all of the big data center companies are walking down this path. I think arguably Google is ahead of others, but Microsoft and Amazon and Facebook and Twitter and all these companies are walking down this path of building their own networking equipment because they couldn't get what they needed from the networking industry. And what they find is as soon as they do this, they have more control, which is the second thing that they want. By making the network more flexible, by taking control, they can determine the features that it has. They can differentiate from the others. So all of the data center companies are able to provide different features from others. And so that's good for them and it's good for us because now they're competing with each other on a more level playing field. When Google first described doing this not inside a data center but between their data centers, they described this about 2 years ago, they said, yeah, we saved a lot of money. But the benefit that we got was instead of having to wait a year for new features, we actually had 4 major updates inside the first 3 months because they controlled the software. Then their software was reduced. The complexity was reduced. The reliability went up. And they were able to then make their network perform as they needed it. So it's pretty obvious where this goes as they do that more and then that technology moves into the data centers, which it probably has. They never actually, none of these companies reveal what they do inside the data centers, so we're not going to know. But it seems quite likely that that's the direction that they're going. Then they will teach the internet service providers how to do it, and then the network and the networking industry will change. Okay, I'm just going to take a digression for a moment and talk about the computer industry. So I've talked about the networking industry. Now I want to talk about the computer industry. So what's been going on in the computer industry in this time, and what can we learn from it? There's a strong parallel here. The computer industry generally is 5 or 10 years ahead of the networking industry in terms of the business structure and the technology that they use. So those networks that we know, this is the IBM 360 on the left-hand side that was introduced on April the 7th, 1964, the time that that picture was taken. They produced 14 models until 1979, when it was superseded by the Z or Z series on the right-hand side. But they were essentially the same monolithic machines, all cost about $1 million each. Then the microprocessor happened. And the microprocessor happened in 1979, primarily through the introduction of the Intel 8088 microprocessor and the Motorola 68000. These processors had about 30,000 transistors on them and operated at about 1 megahertz. But what they made possible was this, the IBM PC. Now, there were other computers around at that time, but as we know, this one really transformed the landscape. It turned an industry that was all about mainframes into all about personal computers. So we know this story, but what happened after that? Well, the next major change on this story that I'm telling is all the way in 2000, as there started to be what are called rack-mounted servers being deployed in large numbers. These are ones from Dell at the top and then HP underneath. But the basic form of them was the same. You could put many of them in a rack. They were low power. Each one of them is 1 3/4 inches tall, and they're quite deep. But you can put many of them and have a lot of computation power, and that's what led to data centers and big warehouses full of computers that we rely on now for the services that we use every day. But then what happened is that people began to realize that those servers from people like Dell and HP, that Dell and HP were essentially selling people Intel CPUs, a little bit of DRAM, a power supply, and sheet metal. There wasn't really any value add from those companies. And so they started to be replaced by the white box servers, which are exactly functionally the same. They're referred to as white box servers because they generally don't have a logo on the front. They're typically made in Taiwan. This one happened to be designed by Intel. It has inside a CPU with 2.5 billion transistors, so 100,000 times bigger than the ones in 1979, running at 4 gigahertz, or 10,000 times, or 4,000 times faster. But that server has a CPU in it. It has a power supply to turn the AC to DC in order to power the chip. It has a DRAM, and that DRAM is running free software, Linux. And then it's wrapped in sheet metal. That was basically it. And so you can imagine what happened to Dell's stock price, right? And so this was between 2005 and 2013, and we know what happened after that. But the important thing that happened to us, for us, on our behalf, by the data center companies was this: row upon row of low-cost servers. And so computation is moving out of companies, out of homes, out of other places, into far more efficient environments inside these data centers. It's a picture of a Google data center in Iowa, and there are many of these around the world. So let's look at what happened to the computer industry over that time. The computer industry went from mainframes based on specialized hardware. IBM built its own microprocessors, using specialized operating systems to control it, complex software to manage the box, and then specialized applications on top, all built by IBM as a vertically integrated box. And the story was, if you want your applications to work, buy your computers from us. We know best. We will manage it for you. It was a very effective story. Then what happened was the microprocessor came along, and you can't sell a microprocessor without telling people how to program it. Wouldn't be much point. And so quickly, on top, people started to build operating systems. The first, of course, was MS-DOS, and that's how Microsoft came about, building to that open interface on that Intel 8088 microprocessor. Over time, an open interface developed on top of the different operating systems. It's called POSIX, and that's how many applications interact with a variety of different operating systems, and so many applications. And so this is what then later turned into the App Store and et cetera that we're very familiar with today. So a vertically integrated business turned into a horizontalized one, sorry for the Americanism, but a horizontalized business which has been cleaved apart or delaminated, therefore providing competition at every layer. As a consequence, the computer industry became much, much bigger. The network industry is just beginning to go through this change right now. So big equipment like this today is built on specialized hardware, specialized operating system, running specialized features. That's the 7,000 features that I was mentioning earlier. And what happened was about 10 years ago, a class of merchant switching chips, merchant silicon, coming from companies like Broadcom, Intel, and Marvell, who were building switching chips. Now, you have to tell people how you program them. And in that case, there was an expectation that control planes or software would exist on top, and that on top of that, a whole load of features would appear under the control of the network owner and operator. And lo and behold, over the last few years, I'm aware of about 16 different control planes that have been created. About 12 of them are open source, and they are the software layer that really makes all of this possible. And so as a consequence, there's a thing called the white box switch, which mirrors the white box server. It looks like this. Doesn't have it has a name brand on the front. It consists of those three things: a microprocessor to do the housekeeping, running Linux, sitting in DRAM, powered by a power supply, but it has this switching chip in it as well. And this white box server, which really just came into existence just a couple of, this white box switch that came into existence just a couple of years ago, has created a furore. Because this is the white box switch which is being used inside all of those data centers in order to interconnect those servers. Now, what does a router actually look like? One of these routers consists of some software and some hardware. The hardware we generally refer to as the forwarding plane. That's how packets are forwarded, packet by packet, hop by hop. But sitting on top of that is the software that I've been referring to, and that software is sitting there communicating with the software operating on all of the other routers. All that software-defined networking is the removal of the software from those boxes, that control plane, out of the network and putting it on servers. That's all it is. So it's taking that software, lifting it up and out into a single location, a more logically centralized location, where it can control those forwarding devices from afar. So when packets come across the network, that software control plane has decided how they're to be forwarded, and it's inserted rules into all of those hardware switches along the way so that the packet will then take its path. The packet doesn't go through software, the packet is being processed in hardware. Software-defined networking is merely a network in which the control plane is lifted up and out and is physically separate from the forwarding plane where the packets are being processed. And a single control plane is controlling multiple forwarding devices. That's actually it. There's nothing else to it. But the consequences are quite enormous because the first thing that happens is it puts the network owners and operators in control of their own destiny. It puts them in control of the network because now that server sitting in the network where the software runs is now their server, and they can choose, where do I buy it from? Do I write it myself? Do I use open source? It gives them suddenly a lot more choice. So just the consequences of taking something that was vertical and making it horizontal means that they now have a lot more choice. It means potentially that networks are more reliable and more secure because they know best how to operate the networks, and so they can make them more reliable by altering the functionality and the features that run on it. Networks cost less because the hardware can return to being simple and streamlined again because it's now being commoditized. And that is essentially what's happening. And the network can cost less to operate because you can throw out all of the features that you don't need and boil it just down to the essence, boil it down to the functions that you need. So let me tell you a little bit about the story of my own involvement in this trend. So while I describe it as inevitable, we played a part, or tried to play a part, in accelerating this change, because there was a group of us that passionately believed that it would be better for the internet and better for the world if this change was to take place. So back in 2007, I had a PhD student called Martin Casado, who was working with me and with Scott Schenker at Berkeley. And as a consequence of a program that we had called the Clean Slate program at Stanford that was looking to answer the question, if you got to start again, start over with a clean slate, how would you design the internet? And we came to the conclusion that really the thing that you needed to do was to make sure that what you intended to have happen in the network actually took place in the network, start from the top, and then work down to a traditional top-down design, like a computer, like how software is designed today. We built a prototype on the Stanford campus. We had about 300 users. We thought this was great. It was wonderful. We were ready to move on and do something different. So we thought, well, maybe others would be interested in this. So we went to the biggest networking equipment vendor, Cisco, and told them about this. And we said, we think this is great. You can have it. It's all open source. You can go and do whatever you want with this. The reaction in the room, and there was about 40 or 50 people in the room, was as we were talking, they got redder and redder and angrier and angrier. And they were saying, this can't be done. This is wrong. This will never work. One of the leaders in the room was so convinced that he actually bet his house with one of the speakers that this would never actually come to fruition. We got into the parking lot, we looked at each other and said, okay, we're onto something, right? You hit a raw nerve and knew that this was just too raw of a nerve to be poking on. And we believed that was the right way to do things, so we said, let's go and give it a try. So in order to encourage some discussion about this, we published a specification called OpenFlow, which really served to have to force this discussion out into the open about separating the forwarding plane, or the control plane, from the forwarding. And so we advocated a network operating system, and the job of that network operating system was to build a global map, a consistent and up-to-date global map of the state of the network, which routers are there, which links are there, which users are there. And then on top of that, a control program, which is just a feature. That control program could decide how it wanted to affect that map, that graph, change it, and then have the network operating system reflect that down. So it would tell it how it wanted to change the state of the network, and then that would be pushed down. So from the top, working down. A network administrator would express the policy that they wanted, who could talk to whom, who was supposed to be isolated from whom, who got more priority than others. That would be expressed at the top and then pushed down. The idea was everything in software as much as possible, and very, very simple hardware. And OpenFlow was the interface that would allow this to happen. In some ways, we were really just driving a wedge right through the middle of that box to try and get that control plane and that software up and out of that box. So we spent the next few years doing a number of things. We published this specification. We started a company called Nicira that was trying to commercialize this, but separately, about 200 universities, with the help of my colleague Guru Parulka, 200 universities have since adopted this as a technology that they use. And I'll tell you about some of the other adoption in a moment. And then we started the Open Networking Foundation. And the Open Networking Foundation has really taken over many of these standards. And now there's about 200 companies, all of the main companies in the networking industry, trying to get behind this change. So it's gone from being sort of a blink in the eye or a gleam in the eye to something that's actually taking place now. Okay, that's the business story. Now let me tell you the technical rationale for this. So what is it that's really behind this change? So really all a router does is route packets to the correct destination. So here's a network. There's hosts A and hosts B, and the routers are responsible for finding the path of packets through to the destination. The software figures out the route. The hardware forwards the packets hop by hop. And the way that the routers do this is by, first of all, telling each other that they're there and telling each other about the links that connect them, so that each one can build a graph of the entire network, so that it can then figure out the shortest path. And in fact, they all communicate with each other in order to do this, to build that graph, and then upon that graph, they try and figure out the shortest path. The most famous algorithm for doing this came from a man called Dijkstra, and he published in 1956 a famous piece of code called, or an algorithm called Dijkstra's algorithm, which is very widely used for finding the shortest path through a network. I'm not going to go through how that algorithm works. As you can see, I can express it in code here, or rather, Wikipedia expressed it in that amount of code, so it has to be true. A very simple algorithm upon which most of the routing takes place in the internet. And I teach it in my courses. It takes about half a lecture to teach a group of undergraduates this algorithm. Very simple mechanism. And it can calculate a route through a network like this in about 30 milliseconds. Okay. So if between A and B, it's going to find a path. Now, the hardware will forward the packets in nanoseconds, so about 6 orders of magnitude faster than the software will figure out the path, but the paths are only calculated infrequently, maybe once every few hours, whereas the packets are forwarded, of course, all the time. So returning to these boxes, the software that's running on those boxes is making the decision as to what the path is. So for example, when packets are going from the left to the right, to be on the right, it's deciding the path that they will take, and then the hardware is responsible for actually forwarding them hop by hop. So let's have a look at what that software is actually doing for this particular function. Well, what is it doing? It's running that Dijkstra's algorithm. But first of all, it has to figure out which routers and links are present. So it exchanges the message, figures out which ones are present, and then it runs that Dijkstra's algorithms to find the shortest path through the network. Once it's figured out the shortest path, it sends down a whole load of rules down to the hardware that says things like, if a packet is going to be, then send it out of port 3. It's turned a global knowledge of the network into a local decision that it can, a local rule that it can tell the underlying hardware. And that's the delineation of responsibility between the software and the hardware. So when a packet comes along destined for B, it'll reach the hardware. The hardware will say, well, I was told that if you see a packet going to B, then you send it out of port 3, and that's what happens. It goes all the way through the network. So those two things that the software is having to do, find out which routers and links are present, and then run Dijkstra's algorithm, are really the only two things that it has to do here. And they're actually defined in a specification called OSPF, or Open Shortest Path First algorithm. And it's one of those standards that I described earlier, number 2328, in that particular version there. And it describes how all of these routers are to do this. And the interesting thing is when you read that document, you realize that 95% of that document is figuring out how you reliably find out what the graph is. And only 5% is running Dijkstra's algorithm. And if you look at the code, so there are 50,000 lines of code that it takes to implement this, about 95% of that code is just figuring out who the other routers and links are. Because it turns out that, although it may not be immediately obvious, building a distributed system with up-to-date, consistent state over a very large area is really, really hard. Running an algorithm over that graph is really, really easy. So building the graph turns out to be very difficult. So this turns out to be a common problem for all sorts of features, all sorts of the features present in the equipment that makes up the internet. So not only Dijkstra's algorithm for figuring out the routing, but other routing algorithms, there's one called ISIS, PGP, MPLS, even firewalls and gateways and security devices, they all are faced with the same problem. So why not have a network operating system that is responsible for building this map and this graph for all of them, rather than them all have to figure it out for themselves and compete and fight? And why not have that network operating system responsible for the state that sits in the devices at the bottom, the forwarding plane? And that's really the technical argument, the main technical argument behind software-defined networking. It is just simply a figuring out who is responsible for what, so that this abstraction of a global network map or graph can simplify the job for the features that sit on top. And most of the time, when faced with this possibility, the owner and operator of the networks throws out most of the features because they don't need them. So how is SDN being used? Well, one measure of how it's being used is what you see in the press. So you will see lots of, if you just go onto Google News, you'll see lots of things like this. And the consequences for companies, not just Cisco, Juniper, Huawei, Ericsson, and as the data center companies start to adopt this simplified form of networking for their data centers and saving themselves lots of money and giving themselves more control. Today's deployments are largely in the networks that interconnect data centers, in other words, the big networks. So the largest networks in the world, the highest capacity networks in the world today are built by the companies that own data centers to carry traffic between them. So many, many hundreds of terabits per second of traffic is flowing between these data centers, and they have built their own routing equipment out of those white box servers, and they're writing their own software to control it. And this is the main way, and this is, there's some lovely YouTube talks from Urs Hotzel at Google and Albert Greenberg from Microsoft explaining what they have been doing in this direction. And everybody suspects that it's happening in the inside the data centers as well. But over the next few years, what we're going to see is public service provider networks. AT&T has been talking about this, NTT, China Telecom, Deutsche Telekom, British Telecom starting to deploy this. Enterprise and campus networks, Wi-Fi networks, mobile and cellular networks have already started to deploy. All products for these areas are all in development right now, which means in the next 1 or 2 years, this industry is going to change quite a lot. Home networks that I put at the bottom, for those of you that have struggled with how to configure your home router, your Wi-Fi access point, you may have wondered, why is it that I have to do this? Why isn't it that the service provider isn't configuring that for me, and so that I never actually have to log in and figure out what a DMZ is or whatever an access control list entry is? Why is it that you have to worry about that? So over time, the software will be ripped out and placed in a more central location. Makes total sense. Hasn't been possible in the past because that's not the culture of the networking industry. It's to put all of that functionality on the box. The thing that's of particular interest to me and my students is that researchers can now try out new ideas in the internet at scale, and I want to show you an example of this, or describe an example of this in a moment. And the basic problem is, there are lots and lots of good research ideas that come out of universities around the world, but there's no way to actually test those ideas at scale, because no one would be foolish enough to let you put your ideas or these features into their network. But once you have a network for which its functionality is defined in software, and that software is well designed, then you can take the risk of allowing new features to be put in a way that is sliced and partitioned and carefully protected from the rest of the features run in the network. But the consequence of not being able to do that today is that there's almost no technology transfer from universities to improve the practice of networking, almost none. So we believe that this is going to change, and in fact, it's starting to change very rapidly now as new features get added. The wake-up call for me was a student of mine, Nikhil Handigal, was very interested in how you could load balance traffic over a network, and he had some clever algorithms for doing this. I won't explain what the algorithms are, but he had no way of testing how this would work in reality. But because the backbone of the internet connecting universities in the United States had been recently upgraded to use this technology, it was then deployed in a number of different universities, and the islands in those universities started to be interconnected by a thing called Internet 2, all using this software-defined networking technology. It allowed him to think of this feature merely as a piece of code that he would write on top of this network operating system. So he ran it in the lab on a server that was controlling a slice of the entire network connecting universities in the United States. The interesting thing was it only took him 500 lines of code to transform the behavior of that network. And I'm going to show you a simpler example in a moment for which I have a brief video. So this was another case. I had a student, KK, who was wondering why he couldn't use all of the network capacity that was a wireless network capacity that was around him. His cell phone had multiple interfaces on it. Why was it that he couldn't harvest and use all of that spectrum and all of those access points and all of those hotspots that were around him at the same time? And you may have wondered the same thing. If you switch on your phone right here, which I think you're not allowed to do, but if you were to do that, you would probably find you can communicate to 20 or 30 different hotspots. And the question is, why can't you use any one of them? Why can't you use all of them? Why can't you use all of them at the same time? There's actually no shortage of spectrum. There's no shortage of wireless capacity. It's that most of it is sitting unused. Wouldn't it be wonderful if we could free up access to a lot more of that capacity, a lot more of that spectrum? So this is a very simple experiment. I'm not going to argue that this is a particularly profound idea, but I want to show you the ease with which this was done. So here's a short video of, this is the Gates Computer Science Building at Stanford. And what we did was to attach a video camera to the front of a golf cart, and we're going to drive the golf cart around the building. So there's two of my PhD students adding that camera to the front. And we're going to stream the video out of the front that's being seen from the front of the camera. We're going to stream it, and then this video was capturing an experiment where that video was being streamed across the United States to the East Coast and being watched live by 300 people wearing military uniforms in that particular case. So in the first demo, we will just run it using the normal Wi-Fi that would operate in the network. That's the sound of the golf cart. And as the golf cart goes around, you can see it's a little bit blocky. That's the view as seen out of the front. And on the right-hand side, you can see the access points that it's connecting to. That little green golf cart is connected currently to one of the access points. In a moment, it's going to reach over and grab onto the other access point. But because the way the network works, the network is unaware of the fact that this is happening. And so it drops all of the packets in the meantime. The laptop running on the golf cart can't actually figure out that the connection has changed. And so as a consequence, it has a momentary loss of video. So the positions of those Wi-Fi access points, those red blocks in the building, what you're probably thinking of is, as based on what I said earlier, why don't I try and use several of them at the same time? So all we're going to do is change the software that's running in the network, not on the laptop, in the network, so that it can figure out all of the different places that it can connect from, and it will spread the traffic over all of those access points coming from the video camera and then send it over the internet. Right now it's connected to 2. In a moment it's going to connect to 3, and as you can see, the video is crystal clear. Now, I've got no way of proving to you that this wasn't a tampered video, but we were so confident that we showed it live. You can see the shadows along. It was done at 7 o'clock in the morning, streaming across the United States to 300 people who were the main funders of the research. So we were pretty confident that it was going to work. So, okay, all very well, nice idea. Surely that would be very complicated. In order to change the infrastructure, well, that entire experiment running on that building, modifying those access points, controlling those access points, was running on a network operating system that was a piece of software that now existed in the network. KK's experiment consisted of 250 lines of code. And I now run classes where the students, the projects, many of them will deploy whole new ways of running the network into our production network in my building, running alongside the production network, without interfering with it. There are many more videos from me and from others that you'll find at this website here if you're interested. So what happens next? I want to describe 3 things briefly. The first one of which is, I don't really have time to talk about this in this talk today. For those of you that are familiar with virtual servers and virtual computers, there is a change called network virtualization that is being deployed in data centers, which I'm just going to skim over today. For those of you that are interested, you can read lots about it online. Networks will become virtualized. The effect of this is to place the data center owners under a lot more control of how their network is used. There's an interesting consequence that has been fascinating me for the last 2 or 3 years and my students, and that is that for the first time, those ideas that have been developed for software engineering for computers can be applied to networks. And that the network itself can be made to be provably correct and apply many of the mathematical tricks and techniques that have been developed for the software industry and for the semiconductor industry to networks. And I just want to give you a smidgen about this. So in traditional networks, legacy networks, most networks that exist today, the control is in the software sitting on the box. I told you that the behavior of the network is determined by rules being pushed down into the hardware so that the hardware can forward the packets correctly. In fact, those forwarding rules dictate the entire behavior of the network. If you know what the forwarding rules are, then you know what the behavior of the network is. So a natural question to ask is, why don't I just go and look at it and see what it's doing, and it'll tell me what the network is doing. The problem today is how that forwarding state, those forwarding rules, gets to be in that hardware. You can imagine that if there are thousands of protocols all running, distributed protocols running on those boxes, all communicating with each other, many of them running on one box, pushing the state down, then it's very, very ad hoc. There is no one location, and this was deliberate, and it was a good thing at the time because of the distributed control. There was no one location for where you could see all of the state, all of the forwarding rules of the network reliably, consistently, and up to date. And so therefore, you couldn't understand what it was doing, and you couldn't reliably control it. It's not surprising these things are so unreliable. There's no observability, there's no controllability. So when packets come through and they're forwarded, the only way you can figure out what those forwarding rules are is by sending lots of packets and figuring out what it's doing right now. And by the time you finish sending a few packets, it will have changed, and you don't know who changed it and why. So all the rules are in the forwarding plane, usually a few million of these rules. I only showed you one, for all sorts of different things, not just the routing. And we never know quite how the rules got there. So conventionally, lots and lots of features and protocols are populating these tables, and these forwarding rules are not observable or controllable. So in this so-called software-defined networking, I'm implying it's some brave new world, but it does really change the perspective for understanding what the network is doing. Because one layer, that network operating system, is responsible for building a consistent, up-to-date map of the network state. Well, that's a good place to start. On top of it, the control programs have their job, which is to modify that state so that they can perform routing or firewalls and things like this, and push it down into the network. So if those forwarding rules came from a well-defined, logically centralized point, then it's reasonable to suspect that we can then go and check whether the forwarding rules at the bottom match what was supposed to be there. Very simple kind of check to be able to do. So it turns out that by having well-defined roles and abstractions, who is responsible for what, we can mathematically prove the correctness across the boundaries. And by those boundaries, I mean, is there equivalence, mathematical equivalence, in terms of what's happening above that line and what's happening below that line across that interface? What's happening between the operating system and what it placed into the network? Is the state that was meant to be put there, that would match the intent of the programmer, actually reflected in the network at the bottom? Because it's all put there by a single entity, the network operating system, and it was all put there on behalf of the control program that was sitting at the top. Once you've got those well-defined boundaries, then you can check and test across those boundaries. This is how semiconductor chips are made. This is how software is tested. This is how software is made correct today. These are actually very, very natural operations to do in many aspects of engineering, and now will find its way into networking. I'm actually going to hazard a guess. I will come back and eat my hat if this turns out to be wrong. In about 20 years' time, the thing that we will look back on and say changed right now, is that networks went from being visible to being invisible, because we no longer had to worry about whether they would work or not. Just as the software on your computer is going from being visible to being invisible, the operating system that's running on your device, because there are many, many clever techniques that are being used to make it correct. The last thing that is sort of occupying me at the moment is that software-defined networks will need to run on programmable hardware. In order to have a software-defined networking, you need to have good hardware, because last time I checked, all software runs on hardware. So pretty much everything is becoming software-defined. Computers, we've known this for a long time. You write software, it gets compiled down to a CPU. We know that story. The graphics card on your computer, the GPU, the graphic processing unit that sits inside the hardware, has been very carefully designed to be built up from a set of primitives that are very good at doing graphical operations. That GPU doesn't know about rendering. It doesn't know about particular pictures. It doesn't know about games. It just knows how to do very simple operations that are to do with graphical operations. Very, very fast and extremely parallel. Software is merely compiled down to be able to exploit that hardware. Cellular base stations, the audio device in your iPhone or phone, also is based on a type of chip called a digital signal processor, or DSP. And digital signal processors are carefully designed to be optimized to perform a set of primitive operations. They don't know about fast Fourier transforms. They don't know about coding. They don't know about cellular standards. They just know about some basic operations that they can do very fast and in parallel. And then software is then compiled to them. I was recently thinking about it, noticing the trend towards electric cars. This is a picture of a Tesla. And in these electric cars, they are essentially a software-defined car. If you look at the chassis of a car, of one of these cards is a bunch of batteries which you can barely see, a motor on each wheel. Everything else is software. And the software even updates every night in order to improve the quality of the car. And you can see that from this platform, in a few years' time, it's on this type of platform that you will then create the application, which is a self-driving car, because the entire car is now defined in software. So what's kind of preoccupying me right now is, so what happens in the network? There is today no such device. There are kind of fixed function chips, but there is no device that is built up out of a set of primitives that doesn't know about protocols, it doesn't know about IP, it doesn't know about the features. It's just an optimized piece of hardware for processing packets in the network. You have to watch the space for this one, because who knows where that one ends up. So in summary, well-functioning plumbing should be invisible. If you never, ever run into anything related to this talk ever again, that was great. If you ever have to think back and say, wasn't it meant to be invisible? Why the hell doesn't this thing work? Then it hasn't happened. So the internet plumbing became too complex to be invisible, which is why we're all aware of it almost every day. This software-defined networking thing, this change, it's a building block, it's a technology, it's a stage of evolution that was inevitable for business and technical reasons. It will make networks cheaper. It will place control in the hands of those who own and operate networks. Networks will become more reliable and more secure, and then with it, they should become invisible. I want to leave you with one quote. I thought this was kind of fun. This is a guy called John Donovan when asked, why SDN? He is the largest purchaser of networking equipment in the world. And he was asked at the end of a talk that he gave just a couple of months ago, why will software-defined networking happen? He said, because there's no army that can hold back an economic principle whose time has come. Thank you. Thank you. Well done. Excellent. Thank you.
Well, thanks very much indeed, Nick. Fascinating approach to bring us all up to date with some things that some of us wouldn't have had any contact with, apart from the fact when the router in the house doesn't work properly. Yeah. But thank you for that. Now, the lecture is open for questions. We've got a little bit of time available, both for questions from the floor. If you want to ask a question, there's one over there in a second.
So I just wanted to say that before you ask any questions, that I've heard this talk before, so it's kind of boring to me. The only thing that makes it interesting is you ask some good questions, so please do.
Please wait for a microphone to come, and if there's a member of staff, could start over there, please. We can also take questions over the internet, so please use the hashtag, and Raphael will wave his hand to me.
Probably won't work. Probably won't work over the internet.
Well, we'll see. It has worked before. When you do ask a question, please keep it very brief. Give your name, your affiliation. If you want to make a point, make it extremely briefly, and a question that can be answered, hopefully, quite quickly too, so we can get quite a few people covered. First one over there, please, to the left.
Thanks. I'm Martin Davis from Voxygen. I'm just wondering if you've separated the control plane from the hardware that does the job, then you've introduced a network between those two parts. So haven't you introduced, a whole new interesting area of failures for when the control system loses contact with the routing system?
Smoke and mirrors, right? Yes. No, you're absolutely right. That if you're going to communicate between a control plane and the forwarding plane, then you need some means to do this. So the biggest networks where this happens today, it's done directly over dedicated links that go from the switches directly to the servers. Because imagine inside a data center, there's lots of servers, they're co-located with the switches, and they essentially directly connect. If you're in a wide area network over many hundreds of miles or many thousands of miles, then they use dedicated channels. So an optical fiber with multiple wavelengths, they'll then dedicate a wavelength for the connection of that forwarding plane back to the software that's going to control it. And that has to be done manually. Over time, there are methods that people have developed that would allow that itself to bootstrap and maintain itself so that that wasn't necessary. But it's a little early days for that. But that will come.
Thank you. And then centre there.
Thank you very much for your presentation. I'd like to ask a question actually about the
Your name,
controllers.
please, and affiliation.
Yes. You mentioned about that your SDN actually separate your, yeah. Oh, my name is Jane Ren. So I'm from CACI.
Nice to meet you.
So essentially, I'd like to ask the question, when you mentioned about SDN, you separate the software from the actual underlying hardware. But would it actually be easier for you to build a unified controller that talks to the network operating system rather than the underlying infrastructure? Because the while the localized, distribution, intelligence that has on the distributed system actually maybe doing a better job rather than a unified computing system, controllers that actually handling everything from a central point of view. Thank you.
It would certainly be an easier, quicker fix to take a number of pieces of existing networking equipment that have hundreds of millions of lines of code running on them and merely put a shim over the top that connects the different pieces of equipment from different manufacturers together in order to be able to control them. If that was your only intent, to provide a unified interface, then you might be able to do that. And in fact, a number of big network operators, some in the UK, some in Europe, some in the US, attempted to do that over a number of years and gave up because they realized that wasn't really the problem that they were trying to solve. They wanted to change the behavior of the network, and the closer you get to the bare metal, the better the job that you can do. And then they came to realize, well, actually, what is the forwarding doing? It's looking at the header of a packet, deciding based on a rule that it matches with the actions that it's going to perform. That's all the forwarding plane needs to do. And so once the penny drops and you realize that that's actually all that needs to happen, you realize that the closer that you can get to that behavior and control it directly, the better the system will operate.
Okay, thank you. One in the centre here, please.
Hi, name is Steve Tuck. Currently, I'm an independent consultant in this area. I'm interested to come back to the thing you finished with, talking about the search for the right model for the network-assisted processor or network function processor. 10, 15 years ago, I wrote code for PowerQuicks from Motorola, which was kind of an attempt at that. I'm interested to know what you think the most successful business and technical models are going to be for the search for that new device.
No, it's a good question. There was some of you may know, there was a type of device called a network processor. And there are probably some people in the room who are completing in the head the fact that if there's a graphics processor called a GPU and there's a central processor called a CPU, then surely there's a network processor, and indeed there is. There was a whole family of devices called network processors. I would distinguish them in the following way. For those of you that took classes in digital design or computer architecture, you will probably remember the day that you saw for the first time the RISC architecture, a 4-stage pipeline or a 5-stage pipeline, for which the functionality was very carefully picked to be the bare minimum that you needed to do in order to perform computation. A CPU does not know about Java. It does not know about Python. It knows about how to do very basic operations really, really fast. So does a graphics processor. So does a DSP. They're completely different in their hardware structure because they're optimized for the primitive functions. Network processors came along, and they were essentially taking a whole bunch of CPUs and throwing them on a piece of silicon and saying, surely I can process packets faster if I do it in parallel. So it was really kind of the lazy approach to figuring out how to do it. And it set back the industry by quite a way, because no one had stepped back and said, what are the primitive operations? What is the essence? What happens if you boil it down to the very essence of the problem? So there are quite a few people that are trying to do that right now, myself included, and a number of others, to figure out what the essence is. And I think we'll have to wait for a few years to see whether that happens.
Thank you.
One from the internet. Question coming from the internet from Stephen Winstanley. Will SDN promote the Big Brother approach of governmental control over network traffic? Would not it affect net neutrality?
It's a very natural question to ask. What happens if you change the nature of control? Doesn't that provide an opportunity for Big Brother or the wrong folks to take charge. Well, there's a lot of evidence that in the absence of that, they managed to take control anyway, so I'm not sure what difference it's going to make. But seriously, I would argue that actually the opposite is true. Today, we have no idea, if we're operating or owning a network, what functionality sits in those 50, 100 million lines of source code running on the equipment in the network. And this is really at the heart of all of the fear that many people in the UK government and even more so in the US government have about Huawei, a Chinese manufacturer who is competing with manufacturers who are building equipment with millions of lines of source code for which you don't quite know where they came from. Now, most of the networking equipment in the world, even from American and European manufacturers, a lot of that software was written in China anyway, so it's a bit of a vacuous argument. But they're worried about this very much today. I would venture to guess that if the owner and operator of the network actually has visibility, particularly if it's open source is open to the scrutiny of anybody around the world to look for bad stuff. Even the NSA loves open source. Why do they love open source? Because actually there's less likely to be bad stuff put in there by other people. Now, open source for the network means that, and it doesn't have to be open source, but open source or any code that is under the control of the owner and operator of the network is less likely to have things in there that were not under their control. Does this prevent that from ever happening? No. This isn't a sort of panacea that's going to remove that opportunity. But in my opinion, it actually makes it less likely, not more.
Thank you. A question up on the far right.
Yeah. Hi,
far right.
David Butler from BBC R&D. I've seen lots of commercial manufacturers now are making OpenFlow capable switches, and there's also kind of the white box ones, and there's lots of open source and also commercial OpenFlow controllers. And there's various other interfaces which are involved with programming switches and things. What do you see as the biggest barrier to interoperability in SDN across all the layers?
So there are two forms of interoperability to think about. There's the vertical interoperability, which is what I think that you were describing in the control plane. So there is OpenFlow itself or any other means. There will, for sure, there already are, and there will continue to be other ways of a control plane controlling the forwarding plane in addition to OpenFlow. It'll be important for them to be carefully specified in the usual ways. And so, look for that to continue, and eventually there will emerge either de facto standards or published standards on top of those control planes for how the features and software runs on top. The other part of interoperability and standards is how the boxes talk to each other horizontally. And that's where most of the standards are today, the wire formats, the particular position that bits are in the packets as they flow to make sure that they can be understood as they go across those boundaries horizontally. That's where nearly all of the standards are today. To some extent, SDN, this whole change, is neutral to that because it merely changes the way it's controlled, not the formats of the packets. So in one sense, what actually I believe will happen is it will make those standards between pieces of equipment much, much less important, because the nature of how these pieces of equipment communicate with each other will be defined in software by the owner and operator of the network. So if you want to introduce a new format, packet format in your network, you can do so long as you don't try and communicate with my network where I might have my own packet formats. You only have to worry about it at the interface between the two. Today, there are relatively few standards that define the interface between your network and my network. Most of them are dealing with the equipment operating in each of our individual networks. So over time, actually those standards about the horizontal flow will become less and less important. In the short term, look for more specifications, more standardization of those vertical standards.
Okay, thank you. Question in the middle there.
Hello, Dave Beattie. I work at Sky. Does SDN have any particular challenges with trying to control efficient multicast environments rather than unicast?
No.
Thank you.
Question up the top there. Something at the back. Good question, short answer. Satisfied.
Jonathan Sturtridge, DMW Group. You described throughout your presentation the network as being quite distinct from the end-user devices at either end. Do you see a day when the network and the devices become one and the devices do the job, essentially, of the network and it gets decomposed into those devices?
So you've discovered the real Trojan horse that's going on here, and that is that as soon as the network is defined in software, and its capabilities are defined in software, that software can now communicate with the software on the end host. So that video that I showed you of that golf cart, I lied a little bit. There's a little bit of software on the end host that is talking to the network. As soon as they're both in software, and that you can modify the software in both places, you can allow them to communicate with each other, and now the network can perform on behalf of the end host, or the end host can adapt what it's doing by communicating with, negotiating with, whatever, with the network. So naturally that will happen, and I would argue that that's a good thing.
Okay, we're running short of time, so the penultimate question there, please, on the left.
John Buckley, an independent. This network hardware that you've got, it has to have some indivisible primitives to protect itself, like from overload or from complex circular routing is just locking the network up. Have you convinced yourself in your research that the job of doing that in the hardware is less complex than the control that you're doing in it at the moment in the traditional system? Or do we have to throw all that away and do unified control of the world?
No, not at all, actually. So the primitives that operate in the network are those which are to do with forwarding packets. Right? Anything that's to do with preventing of loops, preventing packets from circulating forever, is moved to software. And so long as it's in software, if somebody gets it wrong today, then they can fix it tomorrow. They don't have to wait for 2 or 3 years for the next generation of the hardware to come out. So the primitives are really very primitive indeed. And it's usually described as a match action primitive. You match on a packet, some bits in a packet, and then based on that match, you perform an action that you're told based on that match. And so once you've boiled it down to that essence, all of those other things that you worry about get pushed up into software.
I think it's most appropriate that our final question will come over the internet. I wonder whether the questioner has said where they're speaking from.
Yes, this is a question or a comment coming from the Twitter posted by Simon Clifford. The internet was designed to be dumb, reliable, and decentralized, but can it remain that way?
Well, it isn't, right? It's no longer decentralized in the sense that now that the internet has grown, the vast majority of the internet infrastructure is owned by a relatively small number of organizations who are specialized in maintaining that infrastructure. Whether it's Google maintaining their infrastructure or British Telecom maintaining their infrastructure, it's now actually a utility, it's a commodity. And as a consequence, yes, it's in the hands of a number of different organizations, but actually fewer than 10 or 15 years ago. That's only natural. Almost any form of utility goes in that path. And that's really got very little to do with how it's built. But because it's naturally that way, it's better if they have more control, if they have more control over their own destiny, to be able to make sure that it operates as they would wish. And the way that they will do that, they will make it more reliable by making the forwarding more dumb and owning more of the functionality in software that they themselves have created or purchased.
Okay, I'm sorry to draw a halt, but I think our time slot on the TV is probably drawing to an end. Thank you very much for your questions. May I now invite Professor Will Stewart to propose a vote of thanks.
Hi. Great to see you all here. I think I'm here because I chair the committee that arranges these lectures, and I've had a wonderful time tonight. I think the thing I've taken away particularly fascinated me is the trade-off between complexity and the need to simplify. Only connect. That's been a fantastic aspect of this lecture. I have to say, I've actually known Dick quite a long time, and his website that I used to look at, that I had another look at in preparation for this talk, very brief talk, used to be designed by his kids. It was really great, I have to say. It now looks as though it was designed by a Stanford IT department. The content is still fantastic, but the appearance just doesn't have it. Sorry, Nick. I think the whole aspect of the content is tremendously significant. I think it was a brilliantly clear exposition tonight. We actually have an initiative called Demand Attentive Networks, which is looking at the more physical layer. But I need to see how that connects to Nick. We're going to have a talk over that over dinner. But one of the things that fascinated me looking at Nick's career is he really is, to me, the ideal engineer sitting between academia and exploitation, things that really happen, that really make a difference to us, and the intellectual background that goes with it. I think he's fantastic. I wonder whether Stanford do. I noticed that he had to found companies worth several $100 million before they made him an assistant professor. And he had to get into the billions before he made full professor, you know? This is almost as bad as Cambridge. Sorry, somewhere in the UK. But then I looked carefully at his wiki entry, and I discovered what really got him his full professorship. He impressed everybody with juggling balls and reciting pi to 200 decimal places in one go in 3 minutes. So clearly that is what you have to do to make full professor at Stanford. I have nothing to say about tonight except it was wonderful. My only point of slight doubt is he doesn't seem to have a hat. So as opposed to betting your house, this isn't much of a promise, Nick. But I would just ask that we give the best thanks of the institution for Nick McEwan for giving the superb Appleton lecture this year. Thank you.